Hello everyone. I am Projesh Roy from Development Biotechnology at Madras. I thank the organizers for inviting me today, and I'd like to talk about our recent paper on the emergence of self-organized stacks in bidispersed ring polymers. This is the summary of my slides. So I start with some background on what is the theory of ring polymers, and the theory of topological glass. And after that, I will summarize our work on the non-dispersed systems, and then we'll move towards the bidispersed systems. And lastly, I will highlight the effect of pressure hysteresis, and then I will end with the conclusion and outlook. So what are the ring polymers, and what is so special about it? So basically, for the linear polymers, the theory of polymer dynamics is now well established. We will have the reptation model, which broadly explains the movement of linear polymers. But for the ring polymers, it's not yet very clear how this polymers moves. So one can simply think that ring polymers are basically double-folded linear polymers, and that actually helps to understand some part of the ring polymer dynamics. But in this talk, I will highlight that ring polymers poses a much more complex behavior than one can get from this traditional theoretical approaches. So there are very difficult, where the simulation comes into play here, is that synthesizing ring polymers and studying it is actually very difficult because there are chances of contaminations, and one will get different kind of knots and links that forms during the experiment. So understanding the ring polymer dynamics from a theoretical perspective becomes very important in this aspect. So in biological systems, ring polymers are actually has a lot of applications. For example, these plasmids, which are essentially ring DNAs, and they are very useful in biological systems, and to understand their structure and dynamics is essentially critical. And also, for example, in chromosomes, we have these chromatin parts, which are essentially a conglomeration of multiple DNA regions. And people often try to understand how these particular regions are formed, and what are their characteristics. And the recent theory is that these particular regions inside the chromatins are essentially ring DNAs. So they are consisted of different ring polymers rather than linear polymers. And you can see visually that how this linear belt looks like and how the ring belt looks like. And from there, you can say that, okay, it actually looks much more similar for these chromatin ring distributions. So the complexity of the ring polymer starts with the fact that the stress relaxation of the ring polymers are much more slower compared to the predicted from this reptation or different lattice animal models. Basically, what happens is, ideally, one expects that the stress relaxation from this exponential decay, which is shown here. So in this experiment, they have taken the linear and the ring polymers. And you can see that although the ring polymers are faster as compared to linear polymers because they are double folded, but however, this theoretical line, which is shown by this straight line here, actually predicts a much faster relaxation for these rings. However, in reality, they are much slower compared to the theoretical predictions. And the interesting part is that if you incorporate more linear polymers inside your ring belt, it becomes slower and more slower, which is kind of unexplained. Recently, there are some explanation has come from the theory that you can take part of the ring as a linear polymer, and you can basically create a multi-parameter model for this stress relaxation, which partly explains it. But again, there are a lot of questions that is unanswered. For example, is the threading. So the threading in ring polymers is especially special to the ring polymers. You cannot see this kind of mechanism in linear polymers. What happens is you have two ring systems, and they are kind of interlocked into a large length scale topological interactions. For example, you can see here, if you put this ring in between these rings and somehow, and if this rings want to move, it cannot move because this ring is somehow in the way. Although their center of masses are not close enough, which is in traditional glasses, you need to have the particles to be very close together to be packed well. But in this case, the center of mass need not be very close. For example, you can see in this kind of threading, where the rings are actually much far apart. You can take the center of mass of this ring and this ring, they are actually far away. but they form this kind of knots in between them, which arrest their motion related to each other. So it's essentially large-scale topological arrest that forms especially in the ring polymers. We call it a topological arrest in some sense. What is interesting is that even if they are arrested, which means their center of mass does not move, themselves the ring can move around. For example, you can show here that this particular ring polymer is in a very threaded environment, but you can see that there is sufficient dynamics around the contour of the ring. This is calling it a treadmill motion, which is very interesting because it says that the monomer itself has some fluidity. However, overall the system is in an arrested state. So the question is, what kind of glass one can form when you create without explicitly caging the monomer as one does in traditional glass forming systems. So you basically create a network of these threaded or linked rings, and the question is whether this entire system would form a kinetically trapped state. So this kind of system is called a topological glass, where you take unknotted rings and you trap it inside a network of threading. In this case, we are not focusing on the temperature, density, and this kind of parameters that people normally look for in traditional glasses. We are just wanting to make sure that the threading network is maintained in this case. And so there was an interesting paper that came in which proposed this topological glass idea. What they did was they have a system of ring polymers and a system of linear polymers in a melt, and they pin randomly some of the polymers, and basically they make their motion to be zero. So these particular polymers do not move at all, and the rest of the polymers can move around through this network. And what they observe is that the linear polymers, they can escape this kind of pinned network. However, if you take the rings, they remain particularly caged as compared to the linear case. And this is an example of how this topological interaction is controlling the motion of the linear ring polymers and how it is different from the linear cases. They also figured out what is the typical phase diagram looks like for this kind of glass liquid transition, and they predicted that at a very large kind of ring size, one can this kind of pinning will not be required. It will form a glass spontaneously. However, they used a very flexible polymers basically, which is why they got a very large ring size. But we thought that what if we don't need such a flexible polymers? What if we introduce stiffness, and what will happen to this kind of phase diagram? Another interesting part of ring polymers is the cluster glass formation. So what happens is, if you take a very stiff ring polymer, which is almost like a plate or a disc, they often form this kind of column-like structures in the melt, which is not very well described, but you can still identify some interesting clustering of where they are kind of stacked against one another. They termed it as a cluster glass system. And this kind of columns, they can interconnect with each other, which makes it, which can destroy their column structure, but you can still identify some of these column structures. Another interesting part is the ring polymers are depletion effects. So you put ring polymers inside a confined environment, and with a mixture of stiff rings and sort of flexible rings, and you can see that the stiff rings kind of float out of this mixture and they stick to the walls, which means they prefer to be on the walls, which is the depleted region, compared to the inside where it's more flexible polymers are present. So this motivated us to look at the bidispersed mixture of this flexible stiff polymers and what the structures looks like when you don't have the confinement after all. So first we studied the monodispersed systems. So in this case, we tried to introduce pressure inside our melts where the system volume is not explicitly fixed. So we want to see what are the effect of volume fluctuations can take place, how they control the glasses. So we took much smaller ring size than that was predicted by this by the spinning method. We took about 100 Mars systems, and we used the Kramer-West model, which is very traditional for this kind of coarse-grained modeling of polymers. And we used a particular angle constraint here, which is basically the practical prototype modeling. And we simulated the system over a range of stiffness and pressure. And what we wanted to study what are the structures of this system will look like, and what will be the dynamics of this system. First, we observed that as we increase the stiffness, obviously the system structure becomes more open up. So they start from a globule type of system, then they become a more rod-shaped or much elongated structure, and ultimately they become much more plate-like or disc-shaped. Now we wanted to understand how this threading would, how one can quantify this threading effect inside the rings. So to understand the threading effect, one has to know what are the surface area of the rings are. So we analytically calculate the surface area of each of these rings by basically drawing these crisscross diagonals, and our aim is to show that when this particular overlap happens between the two areas, and how can one quantify that how much of this overlap has happened, and that will indirectly will tell us how much threading is present inside the system. And we have devised an algorithm to calculate this minimum surface area. We take care of these loops. Basically, what happens is we're drawing these crisscross diagonals often intersect with these large loops, which creates some error in our algorithm. So we revised our algorithm so that we can identify loops, especially inside this topology, and we can accurately measure the area of the loops itself. And then we basically calculate how much overlap is happening and how much of these rings that is on the even side and the odd side. But this even odd is basically just name we have given. You can also give it plus minus or whatever. So basically, what happens is if it is completely penetrated the ring, then we can say that okay, 50% on the even side, 50% on the off side, which means it is a perfect penetration has happened. So it is a perfectly threaded ring system. And more or less this even side comes up, it will say that okay, this is much weakly threaded system. And we devised a threading parameter which is basically does just that. It counts how many of these monomers are on the even side or on the odd side. And by doing so, we were able to calculate the amount of threading in the system. And we calculated that how many of these threaded polymers are present, which has very high amount of threading, like greater than 0.75 or so. But we say 75% of the rings have penetrated into another ring. And what we observe is that as our stiffness increases, the amount of threading goes up, which means the more stiff the system is, the more penetration happens, and they are much more stable. And to understand this stability, we devised a correlation function which calculates how this threading parameter decays with time. And we showed that by increasing the pressure, one can achieve a very kinetically trapped system where this correlation function does not relax within our simulation time. And we calculated the threading time scale from this analysis, and we have shown that it correlates very well with pressure and as well as with the stiffness as well. So, and we also calculated the diffusion coefficient, and we have shown that this time scale correlates with the diffusion coefficient, or inverse of the diffusion coefficient, and it's essentially linear for the stiff rings. For the flexible ring, we see some superlinearity is present, which might be coming from the packing effects. So basically, in flexible rings, they are much more globule-like, so their threading effects is low. So their blast formation is more controlled by packing rather than threading. However, for the stiff rings, they are mostly linear, which means the threading is actually controlling the slowdown of the systems. So now we come to the bidispersed system. What happens if we take some of the rings inside this melt and I make it into a flexible system? So which was much bigger system. We took 400 rings in cases, and we slowly made some of the rings inside this melt into a flexible with k is equal to 1, and we saw that very interesting structural features emerge. Essentially, what happens is we see that the system becomes more fluidous. So the topological glass that is formed at the pure state, it starts to melt. And there is a spontaneous self-organization happens between the stiff rings, and they start to form this kind of ordered stacks. And this stack formation happens very quickly. Within 20%, we see that most of the rings are forming this kind of well-ordered states. And this local ordering also increases very much, which means the rings themselves or these clusters themselves tend to become very ordered as compared to randomly distributed. So our idea is that ultimately, when it is very diluted, it will form a single stack. I will come to this later in more detail. So we analyzed how the stacks will look like. So first we calculated what is the lowest eigenvector for each ring, and then we calculated that if there are two rings with this lowest eigenvector, what of their angles are. And within some particular cutoff, we determine that okay, if these angles are effectively parallel and they are very close to each other, they are forming a stack. And we define the cutoff for at least 5 or 10 rings are formed this kind of stacks. Then we called okay, this is a stack cluster has formed, and then we can say that all rings inside this stack cluster are essentially stacked against each other. But if that is not the case, then if there is like a 2 or 3 member ring are forming a stack, we don't count it as a stacking effect at all, because that is just some random event that is taking place. What we observe is that within 10% dilution from 20% itself, there is a drastic decreases happened from this amount of unstacked rings. So basically at 0 and 10%, there is a lot of rings that are unstacked, but the moment we dilute it, beyond 20%, most of the rings starts to form the stacks of 10 rings or more. And there are still some fluctuations are here, which I will come later. And so here I want to highlight the dynamics of the systems. And you can see that the bottom part is for the flexible rings, top part is for the stiff rings. And for the stiff rings, at the lower concentration, it is still very much glass-like, where the dynamics is very poor. And then it slowly starts to rise, becomes more gel-like, and then at 80%, it is mostly fluid mixture. On the other hand, for the flexible systems, I find that for the very low concentration of these flexible rings, there is a kind of a subdivision takes place. And more we increase the dilution, it becomes very much diffusive. And this kind of subdivision was very interesting to us because we thought that this might be related to the movement of these flexible rings through the bunch of stacks of these stiff rings, where you can see the stiff rings columns are forming. So if the flexible rings are moving through these particular columns, one would expect this kind of subdivision is taking place. Another part is the threading. So we wanted to understand how the threading decays with time with the dilution. And for this system, we find that after about 50 or 60%, there is a sharp decrease happens in threading. And this is because for this kind of system, we can see that up to 40% or so, there are a lot of stacks, they are interpenetrating each other. So the bunch of stacks are coming in between the other stacks, and that is what is driving the threading up. But after about 60% or so, this kind of overlap between the stacks, they do not take place. So stacks are more parallel to each other, and therefore there is not much threading is happening. So we are effectively melt the topological glass. Now we look at the cluster size distributions. So the idea is that the more dilute the system is, the more rings will form stacks. And now, however, of course, the number of stiff rings are decreasing, so we have to normalize the sizes. And we show that as we dilute the system, most of the rings are forming stacks. Ultimately, when a single stack will form, everything will be at the far right end of this graph, which is 1. But already at 80-20 mixture, you can see that most of the rings has moved to the right side, which basically means that entire ensemble of these stiff rings are forming stacks with dilution. And we also measure how does it dilution controls the angle distributions of this cluster. Basically, what is the local ordering? What is happening at the local ordering? And to measure that, we calculate the largest center of mass vectors between each stacks, and then we calculate the angle between the stacks. And we find that for a pure system, its very broad distribution is there, with a maxima is roughly around 90 degrees, which means that most of the stacks, although there are stacks formation is happening, they are more disordered. However, As we increase the dilution with flexible rings, the graph shifts towards the left end, and they are much more ordered now as compared to the pure systems, which also you can see in these graphs that the pure system is much more disordered stacks are present, but as we increase the dilution, the stacks become parallel to each other, so they are much more ordering. Also at the ring level too, we see that this ordering is happening, which is essentially the same plot as this one. We see that for the pure system there is a broader distribution, and distribution decreases when we decrease the dilution. And then we looked at the stability of the stacks. So basically, we wanted to see what is the stiffness difference required for these stacks to form. And for that, we took one of the structure from the 80-20 mixture, and then we increased the stiffness of the flexible rings. So first it was 1, then we increased it to 5 and 10 and so on. And what we find is that up to 5, this structure remains stable, but the moment we went to 10, this kind of stacks is down, because this flexible, or they are not so flexible anymore, so they kind of compete with the stiff rings. And this competition you can see here, that for this purely up to this 5 stiffness for this flexible rings, it is still, most of the rings are unstacked, but the moment we increase it to 10 or so, a number of unstacked rings decrease for this flexible systems, and opposite happen here. Some of the rings, most of the rings become unstacked for the stiff system, which essentially means that this solvent, it's not the solvent, it's called the flexible ensemble, is becoming more ordered, and at which is competing with the stiffness, with the stiffer rings, and so as a result, this stacks are breaking. And you can see what is the typical shape required for this flexible system, which basically controls this kind of stack formation for this system. What is happening is that for k is equal to 1, it is much more globular shaped, which is helping for the stack formation. But for k is equal to 10, they are becoming much more planar or rod-shaped structure, which does not allow these stacks to form for the stiffer system. So this shape asymmetry has a direct contribution to the stability of the stacks. And then we try to understand this kind of whether the single stack is possible to form at very large dilution. And to understand that, we performed the pressure hysteresis experiment. Basically, earlier, as you can see, there was some fluctuations was there at the large dilution. But whether this is a kinetically trapped state or there is a thermodynamically stable state is possible, that was the motivation for our this pressure hysteresis. So basically what was done is the system, we have taken a artificially created single stack system, and we decompressed up to a very low pressure with some rate, and then we equilibrated it at that pressure, and then we compressed it back to our previous pressure. And this is the result of it. So if we slowly decompress it, it becomes random, then it forms the stacks on its own. So the self-organization that takes place is essentially spontaneous. It looks like two stack, but it is essentially single stack because of the periodic boundary. So this experiment basically tells us that this stacking is essentially spontaneous, and at the very low, very high dilution or very low concentration of the stiff rings, it is possible to form a single stack within the system. So it is a thermodynamically stable state. So to conclude, what I find is that the stiffness plays a very important role in this topological glass formation. And if we adjust the stiffness and pressure, this topological glass can be found for small chains. We don't need very large chains as was predicted from the pinning model. And this binary mixture with a large stiffness difference is basically, it forms a spontaneous self-organization of the stiff rings, which is very novel and different compared to the linear chases. And the stability of the stacks that depend on the stiffness difference. As I have shown, there is a critical stiffness range is present within 5 to 10, which allows this stack to form. They also depend on the pressure and on the shape asymmetry of the flexible rings. And we also recently tried to replace these flexible rings with crowders, and we found that they actually destabilize the stacks, which means there is some criticality, there is some interesting behavior is present for these flexible rings, which is controlling the stack formation. And that is not just a globular shape, there is might be some dynamical explanation is there. And from the pressure hysteresis, we have proven that these clusters are essentially thermodynamically stable states. And for the outlook, there are recently interesting papers was published where they saw the stack formation for these rings which are charged. Essentially, is a polyelectrolyte rings, and they have seen that this kind of stacks also form in this kind of electrical and polyelectrolyte cases, which would be very interesting area to cover. Another aspect is the active rings. So when you introduce active systems, whether this kind of stacks will still be stable or not, that will be an interesting area to study. And we are also looking into these confined systems where you introduce a very thin film type of confinement, and we can study that what kind of stacking behavior will present in these cases. So lastly, I will thank Vani Madam and Pinaki sir for designing this project, and IMSC for providing me the funding.
Just wondering, is the sizes homogeneous when we are synthesizing this ring polymerization things? I mean, the size of the polymer, is it homogeneous? I mean, experimentally when you are synthesizing,
yeah, experimentally it's supposed to be homogeneous.
how do you control? I mean, the size.
I don't know the experimental detail. I think there is related to some temperature related factor is there, but I'm not sure. I don't know the experimental details. But it is difficult to control, mainly because it might form, when you synthesize long chains, it might form knots.
Because there is possibility of the different sizes. So, okay, the second question is, have you tried any heterogeneous, size in your molecular dynamics? So whether the same size is stacking or maybe say intertwining between the different size of the polymers? Have you tried anything with it?
No, I have not tried, but we guess it will be different because it depends on basically the stiffness ratio is related to the persistence length. And when we use a large system, we have to use much larger persistence length, and therefore this difference in the stiffness would go up. So yeah, I expect there will be difference when you use different ring sizes. But we have not tried that, but it will be different.
Thank you.
Any other questions? So I had a question. So you said that when you increase the stiffness, the threading increases, right? So how do you sort of explain that? Is it because it remains in an elongated fashion when the stiffness is
So basically the structure of the rings become much more elongated, as you said, and also more plate-like. So what happens is, if they somehow penetrate into each other, it's very difficult to pull out. Because of the stiffness, they does not have the flexibility to bend itself and then pull out so easily. So for the very stiff system, this kind of threading becomes very obvious, because somehow if you created this kind of threading, it will never come out.
right.
That's the control.
Yeah.
So what is the effect of the interaction strength between the monomer units? Have you checked that?
So we use the traditional
WCA, but like now if you decrease the temperature or increase the attraction, do you find some sort of phase separation occurring?
It can be interesting, but our main motivation is to see the topological effects, and there this interactions will not matter because that is very small cutoff. We are doing like I think WCA is 1.12 or something, that is really small, and these are taking place in for a 100 March system that is roughly the size of 16 or so.
So the constant temperature that you've used, it will not make a difference if you sort of change the temperature.
It will make a difference. It will make the system slower, definitely. But the thing is that what I wanted to highlight is we are not looking into the temperature or interaction strength that usually controls the glass formation. We are looking into the fact just by changing the shape of the rings, whether one can form a glass. So if one can definitely change the interaction strength and temperature, and one will observe different dynamics, but the topological factor will be the similar for all cases. That by changing the shape, there will be a control on the TVR diffusion.
So the threading algorithm you have, can it be applied for detecting the events between linear chain and a ring, for example?
Yeah, it can be done. So basically, this threading algorithm calculates the area of the each ring, and what I measure is how these particular bond vectors for each of these other rings are penetrating from into these surfaces. And so for linear chains, we have the list of bond vectors, and we all have all the list of these areas on these triangles, and from there we can calculate the amount of threading for linear chains.